In this one, we are going to look at measurement. So if you recall from chapter 1, we learned about the scientific method and we discussed how in the scientific method we first go through observation, hypothesis, then we do experimentation, you collect data, and you either revise the hypothesis or you propose a new one. And once you have many hypotheses, you come up with a scientific model or a theory. Now, these observations or experimental data, they can be two types, qualitative and quantitative. And a measurement is a quantitative observation or experimental data. And that's what we're going to be looking at next. So in order to have a measurement, you must compare it to something that is agreed upon. For example, if I want to measure the weight of a sample, like we see in this picture right here, I'm going to compare that weight to either an established measurement like grams or ounces, right? So every measurement is going to give me two components, a number and a unit. So when I look at this, this says it's around a little bit over 1 on the gram side, so it's like 1.2 grams. But if I didn't say grams, you won't know what I'm talking about. So it has the number 1.2 and the grams to indicate what standard I am comparing to. All right, so the unit will tell me what standard I'm comparing my object to, and the number itself will tell me what multiples of that standard object I'm measuring. And in addition to the number of multiples, it's going to contain some uncertainty in the measurement. All right, so let me zoom in here a little bit on this right here. So if you notice that this is the one measurement right here, right? So I am at a little bit above 1, but I'm not sure what this other one is. So I estimated it to be 1.2. All right. So when we talk about uncertainty, it's always indicated by the last digit in our measurement. All right. It's indicated by the last reported digit in the measure. For example, if I were to measure the average global temperature, we usually say it was risen by 0.6 degrees Celsius in the last century. So when we report that temperature increase, 0.6, usually the scientists will report it as plus or minus 0.1 degrees Celsius because it's an estimate. And when we say estimate, we really don't mean that it's bogus. It means it's based on whatever instrumentation you use, that's the best, the closest you can get to the value you're looking for. All right? So the degree of uncertainty in any measurement, and in this particular one, is going to depend on what you're using. So the way you report numbers in a science class, or if you're doing an experimentation, you always record all the certain digits and you always add an estimated digit at the end. All right? So in this case, I have 4 digits that are certain and the last one is estimated. The more digits I have in my measurement after a decimal point will indicate how precise my measurement is. Okay? Not how accurate, but how precise it is. All right? So, and I'll tell you a little bit about the difference between precision and accuracy. So when we talk about accuracy, we're talking about how close I am to the real value. That's what accuracy is. But if we talk about precision, we're talking about how close my value is to the last value I measured and how close it's going to be to the next value. So if I were to measure something, let's say I'm trying to measure the length of this piece of wood right here, this one on top. And if I repeat my measurement over and over and over again, how close my numbers are going to be each other, that will reflect on the accuracy of whatever instrument I'm trying to use. All right? So that's the difference between accuracy and precision. And that's going to be the topic of our first laboratory that we are going to be doing, accuracy and precision. So let's go ahead and try to measure this piece of wood right here. And all I have at my disposal is a meter stick. When I looked at this meter stick, I can, with some certainty, that if I divide it in half, it'll be somewhere around here. This is half of my meter stick. So the actual length of this piece of wood is greater than half, and it's less than 3/4. Okay, this is 3/4 right here. This is half of my meter stick, give or take. So I'm sure it's greater than 0.5, maybe greater than 0.6. I don't know if it's greater than 0.7. It could be. So when I report this, it's somewhere between 0.6 and 0.7 of a meter. So I'm going to record the length as 0.6 plus or minus 0.1 of a meter. Or I can record it as 0.7 plus or minus 0.1 of a meter. Either one of the two is acceptable because it's an estimation of what it is. But if I were to replace my ruler with something with more precision, now this one has a mark tick at 0.1 of a meter. So I know for sure it's greater than 0.5, less than 0.7, it's greater than 0.6, and it's not quite between 0.6 and 0.7, so I'm going to say it's 0.64. plus or minus 0.01 of a meter. All right? So I can write it as such, or I can write it at 64 plus or minus 1 centimeter. Either way. So let's stick with 0.64 right here. Now, if I take this ruler right here down here and replace it with something even more precise, that can give me at a millimeter tick. So what I see here, I got greater than 0.6, but less than 0.65. So it's 0.6, 1, 2, 3, 4, and a little bit over 4. So I know for sure it is 0.64. Then I'm going to estimate the last digit, and that will be 0.642 of a meter. If I were to replace this with even more precise instrument, let me zoom in here a little bit on what we're looking at. So it's actually this tells me for sure that I am at 0.64, 0.1, and exactly 0.2. So I know it falls on the 0.2 mark. When it does that, when it falls on the 0.2 mark, then I know for sure it's 0.642. The 2 is for sure. I can't just leave it. I need to add an estimate to tell the reader, whoever's reading this measurement, to know whatever instrument I use was capable of telling me the difference between this 2, 3, or 1. Therefore, I'm going to add a 0 at the end. That 0 is my estimate here. All right? So anytime you are measuring something, and you're going to be doing that in the lab, you're going to look at the limitation of the instrument. Based on that instrumentation, you're going to record how many digits you have in your measurement. That goes for what we just did here using length. If we were measuring weight, we do the same thing. Notice right here, let me zoom in. It is 1, and it's just slightly above 1, right? It's on 1 right there, and it's slightly above 1. So I'm going to say it's 1.2. The 1 itself, the 1 is certain, and the 0.2 is uncertain. Or this is if I'm using a somewhat a balance like this. If I'm use a balance with a knob with marking every 0.1, then I can even go further. All right, if I measure this, I can look that there is a difference between 1 and 2. I actually can measure 0.1 of a gram right here, so I'm going to add another digit. So it's 1.2 1.26 of a gram. All right. Okay. I have it 1.26 of a gram. So I even can measure further. Okay. So that's what uncertainty in measurements are. The next thing we're going to talk about, reporting our measurements correctly. And we're going to use what's known as significant figures to report measurements correctly. Anytime you have measurements that are certain, they're going to be significant. Otherwise, you won't write them, whether they're certain or uncertain. So all non-zero digits are significant. Then the other part of the measurement is going to be dealing with zeros. So what I'm going to do, I'm going to break zeros into 3 different categories. I'm going to break them into interior zeros, trailing zeros, and leading zeros. Interior zeros are zeros between 2 numbers, and those are significant. Okay, so when I have all non-zero digits are significant, so if I have 4.563 centimeter, that's 4 significant figures. All of them are non-zero digits. So I have 4 significant figures in this measurement. Now interior zeros, if I have 105 kilometer, that's 3 sig fig. That 0 right there is an interior 0, and it is significant. Okay, that 0 right here is an interior 0, and it is significant. Okay, that's interior. So anytime you have an interior 0, it is always significant. Now let me go to leading zeros, number 5. Okay, leading zeros. So when we talk about leading zeros, those are the zeros that fall to the left of the first non-zero digit. Those are always not significant. Okay, we call those placeholders. All right, so these zeros are placeholders. So for example, 0.000, I'm going to represent this value right here in the same way. 4, 5, 6, 3 times 10, 2. So since I'm representing this number less than when it is, so it's 1, 2, 3, 4. So I'm going to put 4 right there, times 10 to the 4 centimeter. Even though that it's not correctly written in scientific notation, but what I'm trying to illustrate right here, that these zeros that we're starting with are not significant. Those are leading zeros. Okay, those are leading zeros, and they are not significant. They're placeholders. I can get rid of them at any time. Okay, they are not significant. Then we have trailing zeros, and I'm gonna break trailing zeros into 2 categories. Okay, trailing zeros are 2 categories. Trailing zeros with a decimal point and trailing zeros without a decimal point. So when we talk about trailing zeros with a decimal point, trailing zeros with a decimal, it doesn't have to be after, with a decimal. So let me actually get rid of the word after, because that's just unnecessary. Trailing zeros are significant if there is a decimal point, and they are not significant if you don't have a decimal point. For example, let me put a new one here. Okay, so for example, for trailing zeros, I can have 1.5000 meter. These 3 zeros are significant, so I have 5 significant figures. So I have trailing zeros. Or I can have 0.05615. So I have 1, 2, 3, 4 sig figs. Those are 4 sig figs. 0.0561500, then that's 6 sig figs. All right, so with the decimal point, we got ourselves significant figures of their trailing. But if I don't have a decimal point, 156,000 kilometer, then these 3 zeros are trailing. Without a decimal point, they are not significant. So I only have 3 sig figs here. All right, 3 significant figures. I hope that is clear. That's how it works. If you don't have a unit, the trailing zeros, if you don't have a decimal point, are considered ambiguous, and we're gonna be careful with those. Are ambiguous and should be avoided. Now, with the reason we are looking at significant figures, it's not important only in looking at how we correctly report measurement, but it's after we have done calculations with our measurements. We need to take into account these sig figs. All right, and that's what I'm going to be sharing with you next. Before we do that, we need to look at exact numbers. So anytime we have an exact number, it's going to have unlimited number of sig figs. And exact numbers fall into 2 categories: counting, or part of a definition. These are the 2 categories: counting or part of a definition or an equation. For example, 1 inch equals 2.54 centimeter. That's exact. That means this has unlimited number of sig figs. Now, why do we care about it having unlimited number of significant figures? So for example, if I give you a measurement in centimeters and I want you to convert it to inches, you're going to use that equality to convert. But when you report your answer, you're not going to worry about how many sig figs are in this particular equality because it's irrelevant. It has nothing to do with conversion in terms of sig figs. You worry about how much your measurement had number of significant figures. That's how it works. Counting, on the other hand, so let's say I have a box and it contains 50 oranges. That's unlimited number of sig figs because when I count them, I shouldn't make a mistake. There are 50 oranges. Even when we do an estimation of counting, it's still unlimited number of sig figs. For example, if we were to look at the population in California, we say we have around 32, 33 million people live in California. Then even though it's an estimation, we don't know exactly until the census is over. Even when the census are over, it's still an estimation because we didn't count everybody. So, but we still consider it to be an exact number. So let's take a look at the following right here. So what I urge you to do is work on these by yourself before you check the answers. So let's take a look right here. Why is this 2 sig figs? I have leading zeros, they're not significant, and I have 2 non-zero digit 2 sig figs. I have 1 interior 0, 1 trailing 0. I have a decimal point. All the zeros are significant, so that would be 4 sig figs here. Non-zero digit, all of them are significant. That's 4 sig figs. 2 non-zero digit, that's 2 sig figs. Okay, this is 2, not 3 right here. Actually, let me fix that right now. It is 2, not 3. Let's make it 3. That's 3 sig figs. There we go. 1 dozen equals 12. That's unlimited number of significant figures because it's part of a definition. 100.00, I have trailing zeros with the decimal point, then so notice the decimal point, the trailing zeros don't have to be to the right of the decimal point. So this right here, I have 4 zeros and 1 non-zero digit, total of 5. All of them are significant. That's 5 sig figs. 100,000. Now, because these are trailing zeros and I don't have a unit, it could be 100,000 people. That would make it unlimited number of sig figs, or 100,000 kilometers. That will make it 1 sig fig. So therefore, at this point, it's ambiguous. Unless I have a unit, it's going to be ambiguous. Now, the goal is for us to record our answer to the right number of sig figs after we have done calculations. And we're going to have to follow rules for rounding. Now, I'm sure all of you know what the rules for rounding are. So if you are rounding, you drop all the numbers. If the first number you drop is 5 or greater, you add 1 to the left of it. And if it's 4 or less, you just leave it out. Okay? Round down if the last digit dropped is 4 or less. Round up if the last digit dropped is 5 or more. When it comes to significant figures and calculations, we're going to have to follow 2 different rules. There's rules for multiplication and division, and rules for addition and subtraction. For multiplication and division, the answer should have the same number of sig figs as the value of the value with the fewest number of significant figures. For example, I'm multiplying the following 3 measurements. 5.02 times this one times that one. When I count the sig figs, I have 3 sig figs here, 5 sig figs here, and 2 sig figs here. If I do the following operation in the calculator, I'm going to get this number in blue right here. But I have value right here with 2 sig figs. That means my answer should only have 2 significant figures. I'm going to drop the 0 right here. It's less than 4. So I'm going to report my answer 45, 2 sig figs. Division, same thing. I'm going to divide this number by 6.10. 4 sig figs, 3 sig figs. My answer should be 3 sig figs. If you do the calculation in the calculator, you get 0.96590. I need to report my answer to 3 sig figs. That means I'm dropping the 9 right here. So I'm going to add 1 to the 5. I reported at 0.966. Addition and subtraction, on the other hand, we look for the decimal place. So the data point with the least number of decimal places will dictate how many decimal places your answer will have. So I'm going to add these 3 values right here. I have 2 decimal places, 3 decimal places, and 3 decimal places. Then my value right here should have only 2 decimal places. So when I add them up, I get 9.214. I'm going to drop the 4. It'll be 9.21. Same thing with subtraction. 1 decimal place, 3 decimal places. My answer should have only 1 decimal place. So I'm going to drop these 2. 0.8. That will be my answer. But most calculations are not going to involve one or the other, but it's usually a combination of both. So the way we apply the rules when we have combinations of both, we're going to follow the order of operation. So always do the steps in parentheses, determine the correct number of sig figs in the intermediate, answer without rounding. I cannot emphasize that enough. Do not round. Always store that value as full while indicating how many sig figs you have at each intermediate step. All right? So you're going to apply the rule at each step, then move on to the next step while keeping the result from the other one without rounding. And I'll show you in a few examples how we do that. Okay, let's take a look at the following. I'm going to take 3.489 times parentheses 5.67 minus 2.3. So step 1, I'm going to do what's in parentheses first. When I subtract 2.3 from 5.67, I'm going to get 3.37. Notice that when I subtract, I'm going to keep one decimal place here, right? One decimal place. One decimal place, two decimal places. My answer should have only one decimal place. If this is what I'm doing only, I would report my answer as 3.34. But since I have a subsequent step I need to do, I'm going to keep it at 3.37. I'm going to underline the 3 to remind myself that I'm stopping at one decimal place. So when I do the next order of operation, I'm going to multiply the two. This one has 4 sig figs, and this one, because it's one decimal place, it's going to be 2 sig figs. So my answer should be 2 sig fig. Notice I applied the rule of decimal places in the first step, then I forget about it. Then I apply the rule of significant figures in the second step because of the multiplication right here. So my answer would be 12. Go ahead and pause the video and try the following. Then come back and check your answer. And then I'll explain. All right, for the first one, I'm doing multiplication and division. So that would be 3 sig figs, 4 sig figs, 5 sig figs, 5 sig figs. So my answer should have only 3 significant figures. When I enter these in the calculator, I get the following value, 0.65219. I need to report that answer to 3 sig figs, so it's simply 0.652. Right here, I'm going to add and subtract. That's 3 decimal places, 1 decimal place, and here 4 decimal places. So my answer should have only 1 decimal place. So this is what I get when I add them all up. Then I'm going to round it to 4.9. Okay, 1 decimal place. I have multiplication, division, and subtraction. So the order of operation would be I need to do the subtraction here first. So when I subtract 452.675 minus 452.33, I'm going to get 0.345. So I'm going to get 0.345. I can't getting stuck. Pen. All right. So I'm going to write the answer to this right here is 0.3455. Now, I have 2 decimal places here, and I have more than 2, so my answer should have only 2 decimal places. So I'm going to underline that 4 right here. My subsequent step is going to be multiplication and division. And if I look at this, I have 4 sig figs here, and I have here 6 sig figs. And in here, that's 2 sig figs. So my answer should have only 2 significant figures. All right? 2 significant figures. Now let's do the next one. The next one, I have multiplication followed by subtraction. So I need to do the multiplication first. So when I do the multiplication, I'm going to get 8.162. Now when I look here, I have 2 sig figs and 4 sig figs. My answer should have only 2 significant figures. Okay, so my answer should have only 2 significant figures. So what I'm going to do, I'm going to line the 1 right here. Okay, so I'm keeping 2 sig figs only. Next step, I'm subtracting 8.02 from it. When I subtract 8.02, I have 2 decimal places, and in here only 1 decimal place, so my answer should have only 1 decimal place, 0.1, 1 decimal place. All right, there are a lot of practice in your textbook end of chapter exercises on this stuff. You should definitely do this. I also have handouts called worksheets. I have them under a heading worksheet in your Canvas. You should definitely download these worksheets and work on these. You need a lot of practice with this stuff. Practice, practice, practice. And whenever we have a meeting, you should come prepared with questions to ask on whatever it is you watched and you don't understand. This is when you come and ask questions.